distinguished lecturer today is Adolf Yonkee, professor of structural geology at New State University. Adolf is a native of Wyoming and got all of his education there through his master's degree, University of Wyoming. And then came here for his PhD, where he was supervised by Ron Bruin and also worked quite a bit with Bill Perry. At the end of that, he stayed on for a little while doing a postdoc on the fault before accepting a position at the State, where he's been ever since 1990, I guess.
Yeah, or the Pleistocene somewhere in there.
So Adolf, I guess what I would say in a general way about his work is this. Most structural geologists seem to gravitate towards either working at the microscopic outcrop scale and deformation processes, or working at the outcrop to regional scale on the geometry and kinematics, sort of tectonic scale of things. Adolf is one of the best at really integrating between those scales, all the way from macroscopic to the regional. And he's worked on a variety of things, but one of the themes going back really to his master's thesis in Wyoming is fault thrust belts. And, this is I want to bring this up partly because the ideas that he's working on testing in South America tie to an idea that's been around since the 1970s, that modern central Andes are an analog for the Cretaceous of this region. And 4 weeks from now, Basil Feedback will be here to give a distinguished lecture. And Basil, I think, has a distinctly different perspective on that issue. So I strongly encourage you to come here, Basil, and see the spectrum of ideas about that. Just leave it at that.
Yeah, and it would be nice if Basil was here and I could be here for Basil and we could
Well, you're welcome. Come visit us in 4 weeks and ask hard questions. Anyway, so I'll turn it over to you.
Oh, thank you, John, for that kind introduction. So today I am going to be talking about mostly on the South Central Andes in Argentina, work we've been doing for the last few years. I'm also going to have a little bit of time where we'll compare it to areas closer to home, the Laramide and the Severe Belt. First, want to thank my colleague Arla Weil at Bryn Mawr College. We've been working in Thrust Belt, Laramide, Argentina for about the last 15 years. He's done most of the Paleomag and the AMS work that I'll be talking about here. I also want to acknowledge support from the National Science Foundation and especially some of our colleagues in Argentina, Dr. Laura Giambiaggi, Jose Mesqua, and a number of students. And I think Ben is somewhere in here, Ben Marconi, when he was at Weber State, was one of the students down in South America. A great learning experience, great international collaboration. So I'm going to start with a little bit on methods, kind of give methods in our madness. Then we'll talk about the Andean system from big scale down to smaller scale. There'll be a little bit of time at the end where we'll then do a comparison to the Severe and Laramide belts in North America. And I want you to keep in mind some questions. What is the nature of the deformation field? And I'll explain that in a little bit, all the components in these different what we call Cordilleran systems, where I'm going to emphasize the importance of subduction. And then what is the influence of this subduction system, plate margin dynamics, but it's also acting on the overriding plate that has a complex original crustal architecture that influences subsequent deformation. And then won't get into as much today, but ideas on what it can tell us about the rheology of the crust and orogenic wedges. So deformation field, what do we mean by that? We mean the components of bulk translation along, say, large-scale faults, rotation, and we're kind of familiar with the one about a horizontal axis where we have bedding as a marker. The one that's a little bit trickier is what we call vertical axis rotation. So imagine this is a bed right here, and I need to figure out how much I've rotated it. Can you tell me how much? No. But if we have a paleomagnetic declination and we know the age of it and its reference, now you can tell me I've rotated it 15 degrees counterclockwise. get that component. So that's why it's important to integrate paleomagnetic information with our structural analysis. Then we also have internal strain, how things distort, and always wanted to use a garbage can, I guess, as a prop, so we'll do that. So you can imagine we have some shape, known shape, and one of the key components is what we call layer parallel shortening. So imagine you have a pile of snow out in front of you or sand and you start to shovel, you can start to see it build up. But before it even breaks out in front, that snow or that sand or that rock is starting to compact. And so we're going to look at changes in shape. It could be by grain scale fabrics. It could be by minor faults, distorting that. And I'm going to keep saying LPS, that's layer parallel shortening. And that's going to be important for our story. So this is an example data set here. So we need to go out and we need to look at everything scale. In this case, here's a cross section constrained by drill hole. So on, as well as getting down to outcrop scale and to microscopic scale. There's 50 micron SEM image. And some of the data that we look at for this internal strain are minor faults, where we can get a slip lineation. Stereo nets, and you'll see a few of these, being a structural geologist, sorry. Bedding is shown here, and we've got two sets of what are called wedge faults. And they are symmetric about bedding. Bedding's been tilted over, okay, but if we untilt bedding back, they're going to be like this. We also have some conjugate strike slip faults. All of them give a consistent shortening direction or sigma 1 direction. We also go in and look at what's called anisotropy of magnetic susceptibility. I can't say that very often, so I'm going to say AMS. And that's related to these mainly paramagnetic minerals like micas that get kinked and rotated. And so the zone axis of these little micro kinks gives us what we call a Kmax or K1 lineation here. And so our shortening direction is perpendicular to that. And so you can see the minor faults. The AMS are giving us consistent patterns, both of them indicating west-southwest, east-northeast, layer parallel shortening. Well, one of the issues is if we get a paleostress or strain direction, has it been rotated from that original orientation? Okay, so have we done something like this? How can we tell? We go to paleomagnetic analysis, and Arlo does a lot of this work. We focus on red beds that have hematite as the main carrier. This is a thermal demagnetization. And then more stereo nets. This is showing individual cores. So we take multiple cores to average out secular variation and come up with a mean direction. Okay, and we have the reference direction, so we can say essentially no rotation, maybe marginal rotation, but that's within 95% confidence, barely so. The diagram here shows that at the same time we get these cores for paleomag, we can also use anisotropy AMS, a bit short. And we start with micas that are along bedding. And it's like a pancake, an oblate fabric, like so. And here this would be our K-min, and our K-max, we don't really get one. Okay? If we start to get LPS, we will start to rotate and kink these micas and give us a K-max that is perpendicular to that shortening direction. We're going to take advantage of that. So I would say most, maybe all mountain systems show curvature at a range of scales. Okay, so here's a mountain system. And the question is, did it start out curved and then just simply get transported and stay curved? So no secondary rotation. Okay, it starts out curved. And just gets transported. We'll use something called a strike test, where we're going to plot the paleomagnetic declination relative to the reference, shown here in these purple areas, against structural trend relative to a reference. And in this case, there's no rotation of those declinations. The strike test slope will be 0. We can also do the same with LPS directions, and in this case, we're going to say it all starts out shortening in the same direction, and it just keeps going. Okay? So that's one end member model, all primary curvature. Another model is what we call progressive rotation. And this will start with a partly curved thrust system related to that primary architecture, and then that gets accentuated as we're undergoing deformation. Okay? And in that case, here's our paleomagnetic declinations. They start out straight, but they get partly curved as the curvature increases. And the strike test slope will tell you how much. So in this case, 50% of the final curvature started out primary, 50% is secondary. We can also do something with the deformation fabrics layer parallel shortening, and in this case, with action perpendicular to this primary architecture, and then that just gets modified during deformation. And if it starts out perfectly perpendicular and stays that way, our strike slope would be 1, and it could be somewhere in between. A final model is where we start out straight, like this, have some sort of deformation, and then have 100% secondary curvature. So straight, and then subsequently oroclinal bending. In this case, our strike test slope is going to be 1 for PMAG and for any sort of deformation fabric that's early. Okay? So we can go out, get paleomagnetic data, get LPS data, deformation fabric data, and test these different models. We're going to be dealing with Cordilleran-style systems. There can be components of accretion of microplates, but we're going to focus on subduction here for this talk. And we have a subducting oceanic lithospheric plate. It subducts because it is denser. Okay? And we can have several different end member scenarios. So if it's denser and the overriding plate is not doing much, okay, that subducting plate is going to have what we call trench rollback. Okay? And if the overriding plate is just sitting there, the arc's going to move with that trench rollback, and the back arc is going to undergo extension as that trench is rolling back. Okay? So we see that in parts of the Western Pacific. On the other hand, if we have an oceanic lithosphere that has an oceanic plateau on it that has thickened ocean crust, it might be more buoyant, at least initially. So this would sort of be like having your come like me in a stick a life jacket on. What's going to happen? I'm going to go flat, and that's one of the ideas behind flat slab subduction. The other component that comes in is the rate of the overriding plate motion. So if we have trench rollback, as long as that overriding plate is moving faster than the rollback, it's going to need to shorten in the retro arc. And here's some models from Liu and Curry. These ones for the western U.S. showing different subduction scenarios. So let's start with this one. We have normal oceanic crust, thick oceanic lithosphere. It's cold, it's dense, it's rolling back. The overriding plate is just sitting there. It's going to actually go into extension. Okay? Here's another one, normal subduction, normal oceanic lithosphere coming down, but now the overriding plate's coming in at about a little bit faster than that. It will actually go into shortening. Okay? Then the other end member is if we combine the overriding plate coming in and we take in this buoyant oceanic plateau, we can get what's called flat slab subduction. Okay? And what is that going to do? It's going to increase the plate coupling over a broad region. So where can we go and test out these dynamic models? Well, one place is the active Pampean or Chilean flat slab down in Argentina, and potentially another spot is looking back in Western North America, back in the Cretaceous, so 80, 60 million years ago. Okay? So for the majority of the talk, I'm going to be focused on this area here. These are contours on the slab going down. Okay? So you can see kind of normal subduction in here. What's happening in here? It's going down, and then it goes flat before it bends over. If you also look at this, you may see that there are these mountain systems sitting in here and nothing down here. So the amount of subduction increases, seismicity increases, and it proceeds far inboard. This shows kind of the focus of our area where we go from the flat slab down to normal. These are some of our sample sites. Need to update for the most recent ones, and we'll be doing probably. So the evidence for the flat slab comes from a gap in the volcanic arc. So these are active volcanoes. Here the volcanoes shut down about 8 to 10 million years ago. Okay. We also have earthquake focal depths that I'll show and tomography from other workers. So that flat slab can be imaged tomographically. It's cold, it's rigid, it's fast, seismically, and it also has a number of deep earth. And then look at our inboard from the plate boundary. Just another picture of that's from another reference, Amirati and others, and here they're using receiver functions as well as tomography. This is the position of the moho here and shows potential offset down here and also some interesting complications within the crust. Another section here, this flat slab going down, the deep earthquakes down around 100 kilometers, shallow earthquakes within the crust. And it's kind of an interesting. The lower crust does not appear, it appears aseismogenic as well as the top of the mantle here. Okay? And there's some sort of detachment in here, and we're going to look at two styles, a fold thrust belt here and what's called a foreland block uplift, thick skin deformation where we're involving most, but not necessarily all of the crust in the same way, but from about 30 kilometers up to the surface. Okay. Give you a little bit of background for plate velocities from some other references here, Somoza and Shidella. And what you see, this is age going back, that velocities were kind of tooling along. This is convergence velocities between Nazca and South America. And then somewhere around 25 million years ago, they increase. And then they've been slowing down, and part of the thought of that is the slowdown's going into deformation. It's becoming harder to uplift those Andes, more work to do. Has been moving consistently westward and may have increased slightly in the last 10 million years. This is the azimuth. It was oblique here, and then it becomes roughly orthogonal, but not perfectly so in the last 20 to 25 million years. The other thing of interest, you may see this is a Google Earth image, these little islands here. There's a seamount above sea level here. This is the Juan Fernandez Ridge, and this is showing its projected position where we think it is today. And that comes from reconstructions, because we know the plate motion and azimuth, velocity here. And so if we go back 20 million years, okay, we just started to become more orthogonal with our motion. And the prior ridge would have looked something like this going underneath. And so from 20 to 10 million years, okay, as the South American plate comes over and the trench rolls back, what's going to happen? It's going to override this. So plate velocities have increased. And by about 10 million years ago, that ridge is coming in orthogonal, and that's the idea that that's also when volcanism, that part, we developed the flat slab. So that's kind of the timing constraints there. So our idea was to go down here and test several different models. You can see this is a pretty classic curved orogenic system. We have a lot of shortening up here. This weird foreland belt in here where we have these basement uplifts, and then a fold thrust belt, and then less deformation to the south. And so one model is that as we develop that flat slab and it moves to the south, okay, what we should see is the shortening rate increase as that flat slab increases, and it ought to migrate southward. And the rotation rate from paleomagnetism should show a transition in here, again moving south with time. Okay? Part of the rollback. Okay, so if I'm in an area that has slower rollback, so the South American plate is coming at a given rate here, this area is rolling back slower, I'm going to have more shortening here than down here if it's rolling back faster. In that case, we expect a fairly consistent shortening rate, decreasing towards the south, and we expect a regional, fairly consistent amount of rotation. Again, with some little local block rotations, crustal heterogeneities. We can also have something where we have highly heterogeneous crustal structure, okay, where we get thin skin deformation in some areas, where we have relatively thick sedimentary strata that are weak. If we get into an area that is more dominated by basement or inversion of pre-existing rift basins, it's going to be stronger, it's going to have lower deformation. So we're going to look at, the idea was going down here to test these different models. We're still in the process of doing that. Kind of the bottom line would be it's a combination of all three. Flat slab's important, differential trench rollback's important, and we have a lot of heterogeneity in the crust down there. Speaking of which, I forgot to mention, put out, kind of keep in mind Mendoza is right here for reference. And we've been working essentially in this area here, and there are three main terrains, okay, big building blocks. Over here towards the foreland is what's called Pompeia. It has a Proterozoic basement. It had an Ordovician magmatic arc, and then it was a basement high. Essentially no Paleozoic strata, no Mesozoic strata. It's not until you get to the Neogene that we get some foreland basin deposits. So this is going to be a basement, thick basement, high region. Then we have something called the Cuania terrain in here. It started with our friends down in Texas, rifted off of Laurentia, and ended up being accreted down here in the early Paleozoic. And so it has a Cambro-Ordovician sedimentary cover, passive margin. It then got accreted on and also overprinted by Silurian Devonian deformation. Okay? So this has a thick sedimentary cover, quite a bit different than the Pompeia, which is basement dominated. And then the final is Chilenia out here, which is a complex mess, Paleozoic arc and back arc rocks, Permian Choyoi group. The northern Neocan basin comes up into here. Quite a heterogeneous pile. So three different terrains with distinct suture zones along this, partly of which these foreland basement uplifts are going to follow, and partly which Triassic rift basins also formed along. Okay? So multiple repeated activations. Just another picture of structural styles here. So here's our Pampean flat slab here. We've got the principal Cordillera, high area in here. This is the Chilenia terrain. The pre-Cordillera, here's a blow-up of that. And it's a typical fold thrust belt, and we're deforming this thick sedimentary package. Okay, so it's sort of like taking your snow shovel on top of the sidewalk, going along, piling up sheets of rock in here. Okay, then we get out into the Sierras Pampeanas, this foreland basement uplift, and this is kind of the structural style here. These are basement rocks. And once we get across this suture, essentially no cover until the Neogene. Okay? So thick end, a lot of seismic activity. It's interesting, though, that it appears to taper off at about a 30-kilometer depth. So the lower crust is deforming a little bit differently than that upper crust. And some of these upper crustal faults, again, are following older suture belts, are basement anisotropies. Okay, so two different styles, thin skin, fold thrust, thick skin, foreland. Timing. So here's our high Cordillera here. Here's the pre-Cordillera fold thrust belt. Okay, and then here's our Sierra Pampeanas. So we start, this is work Teresa Jordan, Julie Fosdick, others have done. But to give you a time frame, we start around 20 million years. Remember, that was when plate convergent rate increased at this latitude. And just like in front of a snow shovel, as you push that along, you get younger and younger thrusts forming out in front. What we call a four-landward younging sequence out to Nickyville, and there's actually a Holocene big fault scarp out there. And then starting somewhere around years, Sierras Pompianas, they start to come up. Okay? Again, that's the time when we developed the flat slab at this latitude. Okay, so again, our areas, we're going to be focusing a little bit, look at Aconcagua Fold Thrust Belt here, the Pre-Cordillera Belt, and the Sierras Pompianas. Done a lot of sampling. We have 350 some sites so far, I believe. And just show you some of the styles. So here in the principal Cordillera, that is Aconcagua, highest point in the Western Hemisphere and Southern Hemisphere. And we have deformed, these are Neokin Basin rocks, Jurassic Cretaceous strata in a fold thrust belt here. Going to the Pre-Cordillera, these are thick Cambro-Ordovician carbonates thrust over Neogene strata here. And then the Sierra Pompianas, I could show a picture from the northern Wind Rivers. It would look very similar to this. The vegetation would be a little different, but classic basement involved foreland structures. So we look at the big scale. We also look at the mesoscopic to microscopic scale. So here are some outcrop photos from somewhat smaller. There's me for scale. And what's going on here? So this is one of the thrust faults in here, putting Miocene over Pliopleistocene deposits. Okay, following this along strike, this fault system was the site of an 1860 magnitude 7.5 earthquake roughly that leveled Mendoza. At the time it killed, the estimates are about 3/4 of the population. These are examples of what we call wedge faults. Remember those that are acute angles to bedding, so low angle reverse faults. That's that early LPS. Sometimes we get that. Sometimes we get folds in here along with reverse faults, and same over there. So this LPS is pretty extensive, particularly in the Pre-Cordillera part. So this is a Google Earth image, and it looks like I forgot to put a scale. That's roughly 100, 200 meters, something like that. Maybe the scale here. There it is. Okay. I always like to show the first picture and then the interpretation. So this is in what's called a triangle zone in front of the Pre-Cordillera fold thrust belt. And now, rather than seeing reverse faults, wedge faults, we're looking at map view, we're seeing strike slip fault. Okay, so structure quiz. Who's had structure? Here. So when we look at conjugate wedge faults, reverse faults, the shortening direction is the acute bisector, right? Sigma 1 horizontal, sigma 3 would be vertical. Okay. How about with strike slip faults? In the acute bisector is going to be our shortening direction, sigma 1, and now sigma 3 is actually along strike. So we see both types of faults. And this happens also in North America. It happens in the Alps. It happens in Iran. And it's interesting that we see this. And both the strike slip and the wedge faults give us a consistent shortening in sigma 1 direction. But what we see is an interchange between sigma 2 and sigma 3. Okay? That is for things that go from kind of out, 100 meter scale. But when you look at the overall orogenic scale at tens of kilometers, remember the cross section? It's all reverse faults. So why do we see this change in kinematics of faults when we go from kind of mesoscale to macro scale? I don't have a good answer, so you can ask that question later. This is an example data set, Nickyville anticline here, so an individual outcrop. Bedding here is near vertical, and we have faults that sit like this, and in their current orientation they're normal faults, but you tilt them back and they become wedge faults here and the strike slip faults, and again all of these will give you a consistent shortening direction. We also have sampled the red beds for paleomagnetism. There's Triassic red beds in here and some Permian ones. A little bit of Cretaceous, not much, and main focus has been the Miocene. We're still in the process of getting all of the PMAG done. We've gotten most of the AMS work, and so I'll show you some results from AMS fabrics and from the minor faults. Okay, so AMS fabrics, remember those? Okay, this is related mainly to paramagnetic phyllosilicates laid down along bedding, and here's bedding in all of these ones, and then here's bedding restored to horizontal. This is going to be our K-min, okay, perpendicular to like layering in the 001 plane for micas, and then K-max are these ones right here, okay? And so the idea is we start with the bedding fabric. This particular sample, rotate bedding back, you see K-min here, and K-max, K-intermediate, they're just kind of like all over the place. That's dominantly a bedding fabric. Okay. This one's been restored. K-max here has a nice clustering. That's the zone axes of those kinked micas. Okay. And that gives us a nice shortening direction. Here's another one. And here the K-min is actually coming off of the bedding pole here. And so this one we've had LPS, but we've also modified it by shortening probably on a fold limb after bedding has been tilted up. Okay. Paleomag data. Some things are very well behaved. These are demagnetization plots showing the horizontal and vertical components. And I'll show you a little bit later how we can plot these on a stereo net and get an idea of inclination and declination of our paleomagnetic vectors. We see reversals. We see mostly well-behaved behavior. Once we get above a high temperature, this low temperature stuff is a viscous overprint. And this is kind of how my office looks right now. So not all samples work. Truth in advertising. Okay, so what we're going to do is take a brief tour of an area in the high Cordilleras, a little bit in the pre-Cordilleras. The data in the Sierras Pampeanas has been hard to get, so we'll take a brief look at that and then summarize things. So starting in the Aconcagua area, this is supposed to show one of these wedge faults, so bedding's tilted here. Here's a little see this pattern of conjugate wedge faults, some conjugate strike slip faults, also called tear faults, consistent with early LPS. Okay. Then as we go on with more deformation, we start to fold and thrust things. Concentration of deformation on larger, weaker fault zones, dominantly reverse slip, and we reorient those early fabrics, and in some cases we get a secondary set of faults over printing. I'm not going to talk about those today, but in some areas we can get paleo stress directions over a protracted history. We're just going to deal with the early LPS ones today. So this is Aconcagua fold thrust belt. One of our students, Michael Garlick, there for scale. Aconcagua in the background. And these are directions from minor fault networks in red and from AMS fabrics in white. Okay. And we see a pretty consistent pattern, and the shortening directions are kind of fanning about, going with the structural trend. Okay. And dominantly overall east-west shortening to a little bit north of east. Okay. So pretty nice pattern, and you can see the structural style here of these repeated stacks of thrust sheets of, in this case, Jurassic and Cretaceous strata. Now we'll zoom in a little bit on the Precordillera here, a couple of places. This is Waco and the Mogna area. So here, geologic map. Here are shortening directions for minor faults from AMS fabrics, and overall pretty good correlation. Okay. And overall direction is west-northwest, east-southeast shortening. Here's some of the data that goes into that, minor fault data, AMS, and from that we take bedding back to horizontal, get our shortening directions and plot them up. Also shown here is the paleomagnetic data for this area in situ. So this is where we drill the cores off a fold limb or whatever, okay? And then what we call tilt corrected, where we take bedding and go back to horizontal. So if the paleomagnetic our vector was acquired before folding, okay, then if we untilt things back, we should get maximum clustering, because as we fold, we're going to cause increased dispersion. Okay, so we need to know the timing, and this fold test tells us that the magnetization was acquired prior to the deformation. Okay, and you can see there's a fair amount of scatter still, but increased clustering. So we do have some local block rotations, and we do see a overall change in the mean orientation of what we measured compared to the reference direction. It's not a huge amount, something on the order of 10 degrees. An individual site, you wouldn't get it. We have to use the statistics of large numbers to average out a lot of the structural noise, the local block rotations. But overall, a net small rotation in the area. This is Mogna area in here. Again, some more minor fault and AMS directions. And again, pretty consistent pattern. Overall, east-west to east-southeast, west-northwest. Only going to show one strike test plot for the some more up this morning, ran out of time, but this is LPS versus structural. And similar, a slope close to 1, meaning our shortening directions are very closely tied to structural trend, roughly perpendicular. Now we're going to step back and take a little bit larger view. And it's going to include some of the Sierra Pompeianus out here. We've had maybe 75 sites out there, and only a handful of them have actually given us good shortening directions. And so, the amount of LPS out there is much less. Also, the amount of shortening. Just back up here. When we looked at a cross-section here in the Precordillera way back when, should have pointed out, the amount of shortening is about 65%. Meaning if we started with something about 300 kilometers wide, it's now 100 kilometers wide. We've had 200 kilometers of shortening. And those thrust sheets are stacked actually not one on top of another, but one upon one upon one. So there's a tripling of the section there. When we get to the Sierras Pompeianus, on the other hand, we're looking at a few percent shortening, so much less amount of shortening, and also much less LPS, okay, with that early internal strain, less than 1%. So it's hard, you have to really work hard to find it. So this is the idea. Out in the Sierras Pompeianus, the amount of LPS is like pretty marginal. We do our best. We might find a wedge fault in one outcrop and go somewhere else and maybe find one wrench fault. Very limited. The AMS, just a very few handful of sites actually gave us a measurable Kmax lineation. Most of them still had sedimentary fabrics. And then we get large-scale fault slip again out there. It's kind of in its youth. We're only looking at something on the order of 5% or less total short. So here's a regional map. Here's the Pre-cavity airfold thrust belt, we were looking at data up there and down in here in those previous slides. This is a more regional data set. Mendoza is sitting down in here. San Juan here for reference. And you can see what we have in the Sierras Pampeanas. Going to try and get back this year sometime and see if we can get some data up in here. Basically, the pre-Cordillera, the overall shortening is east-west to east-southeast. And in the Sierra Pampeanas, maybe a little bit more east to northeast. So these ones are following roughly perpendicular to the structural trend of the thrust and to the topographic front. These are not quite parallel to, but closer to the plate convergence direction, which is going like so. And the other important point here is that we've looked at both Miocene red beds, Triassic red beds, and we get robust and consistent fault and AMS fabrics in the pre-Cordillera, and where we can get data in the Sierras Pampeanas, we're getting more or less a consistent pattern. Just need to get more data. I want to just take a little bit of time and talk about how we date our Miocene information we've been documenting with current Holocene deformation, and actually more recently than that in this century. So these are GPS velocity field vectors. That's about 6 millimeters a year there, something like that. And what do you see? So here's the plate convergent vector. There's generally a parallelism with these, but this is at roughly 6 centimeters a year. These are at 5 to 10, 12 millimeters, 15 millimeters a year back in here. Okay? And what's happening to the amount go to the foreland? It is decreasing. So the key in a velocity field is not the absolute velocities, but the gradient, the change in velocities. Similar if you're driving down the street and you're going 30 miles an hour to the north, what's important is what that point in front of you is doing. Is it going 20 miles an hour to the north or 40 miles an hour to the north? It's the gradient. Okay? So we can plot these and fit models to them, and what it tells us is that we have a gradient going, this is our east velocity component versus east distance. Okay? And it's decreasing that way, so if this is moving faster, this is moving slower, what's going to happen? I'm getting convergence. Okay? Devil's in the details. Part of this is related to large-scale plate coupling of that overall tectonic zone and locking along the subduction boundary. Okay, so there's some issues in removing that, but bottom line is there's still a component left over. We can debate how much. It's going to be less than this, but something on the order of 5-6 millimeters per year, which matches the long-term shortening rate we get from the pre-Cordillera. Is a east velocity versus north distance. This is a wrench shearing. So the amount of slip at the same distance from the trench is greater up here than it is down here. Okay, so there's this wrench shearing that could be accommodated in part by rotation, that vertical axis rotation. And if you fit this and back it out, you get about a little under 1 degree per million years. Okay, and we've been going for between 10 and 20 million years, depending on what part of the belt here, and we've seen roughly 10 degrees average rotation. So again, it works. It seems to be a consistent pattern. Now, we can't get into kind of details of temporal variations, but over the last 10 to 20 million years, we've had a fairly consistent kinematic pattern there since the onset of that slab subduction. Earthquake focal mechanisms. These green arrows are the shortening directions from those. I've plotted a few of these from various workers. These are reverse fault mechanisms here. Some of these get down to, some of these are magnitude 7 up here, that one. In the 1940s, a lot of damage to San Juan. Mendoza down here, we don't have a focal mechanism from the 1860 earthquake, but they do have the fault scarp and can look at that. It also is a reverse mechanism. There's also a handful of strike slip. Most of these are around magnitude 4s. But again, these are the shortening axes for those, pretty consistent. So focal mechanism data, these are averages for our LPS that we've gotten. So we're averaging by domains and broadly a consistent pattern. Okay. Again, east-southeast shortening here in the Precordillera, a bit messier here in the Sierras Pompeianas, and there's some stress refraction appearing correlated with basement faults in there, so then possibly with basement weaknesses. So that's the summary, putting all of the data together. And we're still collecting more data, particularly we want to get up in this area. But overall consistent pattern with what we're getting from minor faults, from AMS fabrics, the gradients in the GPS velocity field, earthquake focal mechanisms, and a difference between the Sierras Pompeianas and the Precordillera fold thrust belt. And so just summarize some key concept from the Andes, and then we'll take about 5 minutes or so to look at the North American Cordillera. So we saw an increase in convergence rate about 20 million years ago. That's the onset of significant shortening in the Precordillera fold thrust belt and the Aconcagua fold thrust belt. Okay. Then by about 10 million years ago, we see development of the flat slab. May have propagated somewhat to the south with time. And this is the time when the Sierras Pompeianas start coming up, and we see a broader range of deformation. Much different structural style in the Precordillera, where we had thick sedimentary rocks, thin skin fold thrust belt. Sierras Pompeianas, the Pompeia terrain, thick basement, no sedimentary cover. The stress transfer in the fold thrust wedge is roughly perpendicular to that topographic front and to the structural trends of the thrust faults. Whereas in the Sierras Pompeianas foreland, it's more varied and closer, but not quite along the plate convergence direction. And some of this variation in the foreland is probably related to basement weaknesses and stress refraction. But again, need more data there, it's just hard to get. So 5-minute quick comparison to North America. So this is where we got started, and the advantage here is we have, like 100 million year history preserved. We have thicker sedimentary strata in the foreland, so more markers we can use. What we lack here, though, is this is a conceptual model. We don't have, the image of what the slab looked like. But the idea is, and you'll have Basil Teacoff give maybe a different version here, but one of the models is we had an oceanic plateau come in starting about 90 million years ago, the conjugate to the Shotsky Rise, which is still preserved out in the Western Pacific. And the plate reconstructions bring it in here, and then coming in, and plate motion would have been more oblique in our setting here, more southwest, northeast. It came in, disrupted, and worked its way up towards Wyoming. And this oceanic plateau, the idea is made flat slab subduction. We shut down the Sierran Arc. We had some interesting patterns with subsidence in the foreland, and then we start developing the Laramide foreland upwards, which overlap with the end of the severe fold thrust belt. So just comparison in styles. This should look familiar. Here we are. Image, and you can see again a curved fold thrust belt. Typical thin skin structural style. We're taking our snow shovel, shoving the snow or the sediments off of the basement. Here it's about 50% shortening. Total shortening is around 200 kilometers. We do have a little bit different styles of internal strain. Here we actually start getting ductile deformation, deformed reduction spots, space cleavage, vein arrays, because we've eroded the level. So we're seeing a little bit different mechanisms, but same idea of this importance of layer well as shortening early in the history of each thrust. Laramide foreland, anastomosing basement uplifts, similar style to the Sierras Pampeanas. Cross sections, again, thick skin style. Models here, I should have had maybe a slightly different cross section. There's evidence that this becomes flat somewhere down at around a 25 to 30 kilometer depth. There's no evidence for offset of the moho in the Laramide, so again it appears the lower crust is shortening by some different distributed mechanism compared to the middle and upper crust that have these discrete reverse faults. Internal deformation again is less in the foreland, but greater here than what we see down in the Sierras Pampeanas because we have a little bit more sedimentary cover, a little bit easier to do things. This is a comparison of Laramide LPS directions from, again, AMS and minor fault data and from the severe belt. And in this case, it's a little more dramatic difference in South America, and that's probably because the plate convergence direction for here is more to 80 degree angle. Here we're looking at 50 to 60 degree angle. Okay, and so again in the fold thrust belt, shortening directions are perpendicular to that topographic and structural profile. Okay, whereas in the foreland, okay. So you can see the significant difference. And part of the variation in here is related to secondary rotation that we'll see. And you can see some variation in here. These tend to be at high angles to the arch trend, is related to stress refraction and basement weaknesses. PMAG, systematic rotation in the fold thrust belt related to differential shortening. The Laramide foreland, no systematic rotation. And so this is kind of the model we come up with for the Laramide and the severe and comparison to South America is that we have flat slab subduction that's important, and that is providing some sort of basal coupling, okay? It could be directly from on the lithosphere, it could be from induced asthenosphere flow, it could be partly from end loading, but somehow you've got to get that stress transmitted through the overriding plate lithosphere. And a different style in the upper crust compared to lower crust and mantle. Severe fold thrust belt, again, has a component of topographically induced stress as well as end loading. So, been doing a lot of work over the last, I guess, 15 years it seems like with Arlo, and we still have a ways to go. It's been important, I think, that we've integrated paleomagnetism with structural analysis. It gives us a more complete understanding of the deformation field, and we've applied this both to thin skin belts and to thick skin belts and to areas where we have current as well as inferred past flat slab subduction. Okay? And these patterns appear related to the plate margin dynamics and to inherited crustal architecture. In fold thrust belts, thin skin, topographic stresses, and presence of weak layers in the sedimentary cover are important, whereas in thick skin basement-involved forelands, part of that stress transmission is coming from that flat slab at depth. Exactly how that's happening is still uncertain. There's evidence that will result in partial removal of the mantle and increased coupling, and there's some devil in the detail differences in the nature of lithosphere between North America and South America. But key is having stronger, colder lithospheric mantle that can transmit that stress through it. What's happening in the uppermost mantle and the lower crust, be curious if people have some ideas. But anyway, and I will stop there.